Very good morning and welcome you all to the NPTEL course on Economic Operation and Control of Power Systems. I am very sure that you must have enjoyed my previous lecture where we talked about locational marginal costing, multi-area transactions and the benefit that we get due to interconnection and interchange of energy. And today we'll be talking about multiple utility interchange and mostly we'll be focusing on wheeling of power from different resources. Now, phenomenon that take place with multiple utility interchange is popularly known as wheeling. That means you wish to wheel energy from one area to other using different utilities facilities. Now, wheeling is the use of some party's transmission system for the benefit of other parties. Because I am an energy owner, I do have 5 power plants and I do have another industry which is located 500 kilometers away. So I wish that my own energy need to be used at my industry location, but I do not have transmission corridor. So I have to use someone's transmission corridor to exchange my own power, okay? And that is possible through wheeling. And the power not necessarily move as you desire because it depends on system conditions and the line constraints. It occurs on an AC interconnection that contains more than 2 utilities, more popularly 2 different parties. Whenever transaction take place, if there are only 2 parties, there is no third party to perform the billing here. Now we'll just concentrate on one very interesting example which has been very detailed in the textbook on Wood and Willenberg, wheeling and the problem of parallel path. Now consider the example which has been shown in the diagram 32.1, that is basically 6 locations A, B, C, D, E, F. Suppose area A and C negotiate to sell 100 megawatt through A to C. That means there is a negotiation between 2 different parties. That means C is ready to buy 100 megawatt from A and A is ready to sell 100 megawatt to C. So to me, there could be an industry in this zone, all right, and there could be a generation at location number A. So this fellow, gentleman who generate power, instead of selling to the grid or the utility, the gentleman at A is interested to sell power to a consumer situated at location C. Now, area A will increase its schedule net interchange by 100 megawatt because whatever the earlier energy exchange that is coming through A will now increase by 100 megawatt and C will reduce its net interchange scheduled by the same amount. Assuming there is no losses in the system, so you basically increase this by 100 and reduce this by 100. So this is consumed and that is being generated. Now the generation in A will increase by 100 megawatt cell and that in C will decrease by the 100 megawatt purchase. Okay, that's what numerically we add and reduce will lead to cell and purchases. Now in the figure 32.2, which shows the resulting changes in the power flow because of increase in 100 megawatt and reduction in 100 megawatt. And as you could see, now at this location we have increased 100 megawatt and this 100 megawatt has now flown this way 50, that way 50. And now this 50 is divided into 25, 25 and 25 and this both merged to 50 and moving to 50 and finally C got 100 megawatt as an additional energy. And A has penetrated 100 megawatt. Note that not all the transaction flows over the direct interconnection between the 2 systems. Initially we thought that the 100 megawatt will flow in this line because we are talking about the transaction between A to C. But in reality that is not happening. Even though I wish to exchange power between Jaipur and Ahmedabad of X megawatt, it is not necessarily the tie line connected or the interconnection between Rajasthan and Ahmedabad will carry that X megawatt transaction between Jaipur and Ahmedabad, but it may go through some other path and may enter to Ahmedabad through Bombay or Pune. It is possible, am I right? So A is selling 100 megawatt to C, but all the other interconnected areas are affected. So it is not mandatory that if there is an energy exchange that is between A to C, only this corridor is going to get disturbed, but all the other corridors got disturbed because of one transaction. Is it clear? That means we can conclude that the energy which has been willed through different corridors to reach to C to satisfy the transaction of 100 megawatt between A to C, and that is clearly known as billing. The number of possibilities for transaction is very large because this is a very simple example of 6 areas or 6 buses. But practically any country, for example India, which is very, very big and very difficult to identify how the whole transaction got disturbed. So if you introduce an interchange of energy or an exchange of energy into an existing optimal power flow or a load flow, you will experience each and every line will experience a different power flow now. That means because of the transaction, the power flow in each and every corridor oscillates because of the new transaction. The number of possibilities for transaction is very, very large. And the power flow pattern that results depends on the configuration and the purchase sale combination plus the schedule in all of the systems. As an example, in United States, various arrangements have been worked out between the utilities in different regions to facilitate inter-utility transactions that involve billing. These past arrangements would generally ignore flow over parallel paths, where the two systems were contiguous and owned sufficient transmission capacity to permit the transfer. Difficulties arise when billing increases power losses in the intervening systems and when the parallel path flow utilize capacity that is needed by a billing utility. Now, what exactly happens when you carry out a transaction? There are two challenges. One, that may increase the system loss, that is one, and probably there are many parallel path flow that really is supposed to be utilized by billing being utilized by its own loop flow that takes place within your network. Now, increased transmission losses may be supplied by the seller so that the purchaser in a transmission receives the net power that was purchased. For example, if I am purchasing 100 megawatt and that leads to a loss of actually 10 megawatt, then the seller will inject 110 megawatt so that I get at least 100. The other arrangement could be the seller will give 100 megawatt and the purchaser will get 90 megawatt, accommodating the losses. But in general, the seller take the responsibility to adjust the losses that is being caused or created due to the transaction. In other cases, the transaction cost may include a payment to the billing utility to compensate it for the incremental losses. The relief of third-party network element loading caused by billing is a more difficult problem to resolve. If it is a situation that involves overloading a third-party system on a recurring basis, the utilities engaged in the transaction may be required to cease the transfer or pay for additional equipment. Loop flows and arrangements for parallel path compensation become more important as the demand for transmission capacity increases at a faster rate than actual capability does. This is the situation in most developed countries. New high voltage transmission facilities are become more difficult to construct, that we all know. Another unresolved issue has to do with the participation of organizations that are basically consumers. Should they be allowed access to the power transmission network so that they can arrange for energy supplies from non-local resources? In the deregulated natural gas industry, in the United States especially, this has already been implemented. Now, when the expansion of phase angle regulating PAR transformers, flexible AC transmission devices, back-to-back HVDC links, and long-distance HVDC links enable more control and more flexible. So these are the devices which can control the power flow in a network. For example, if the line is getting X megawatt of power, they can increase to 2x or 3x depending upon those flexible devices are being engaged in those corridors. An HVDC system is presently proposed to overlay the present AC system within United States corridors. Even in India, many HVDC corridors are in project mode now. European Unions and China have also planned for extension of HVDC system to make sure that the AC system is able to accommodate more renewable energy sources which are currently coming up. So if you look into the Indian network today, we have also created a green corridor now which is responsible to accommodate all the renewable powers that are available, which has never been planned before 50 years. So due to the new presence of renewable energy sources, we need to have new corridors to evacuate all the energies that are presently available to me, either in desert areas or maybe in coastal areas due to wind energy availability. Now, wheeling is inherent if utilities can contract beyond immediate connections as implemented in the system, especially the western half of the United States through the Western Electricity Coordinating Council. And similar kind of structures is also available in Europe, China, India, and most of the developed nations today. East Coast interchange was only between interconnected immediate neighbors. However, the density of the transmission system and the lack of flow control has shown that wheeling is inherent also in the eastern half of the United States. So wheeling is a quite common phenomena in North America, and however, in a market shape actually, the other Asian and European countries also concentrating on such kind of energy exchange in the current stage. Most power systems are interconnected with all their immediate neighboring systems. This may mean that one system will have interchange power being bought and sold simultaneously with several neighbors. In this case, the price for the interchange must be set while taking account of the other interchanges. Dear students, you'll be happy to know there are two exchanges currently operational in this country. And in India, we do have two exchanges which carry out and accommodate different wheeling as well as sell and purchase of power between two different entities. For example, if one system were to sell interchange power to two neighboring systems in sequence, it would probably quote a higher price for the second cell, since the first cell would have raised its incremental cost in the beginning. In the other hand, if the selling utility was a member of a power pool, the sell price might be set by the power and energy pricing portions of the pool agreement to be at a level such that the seller receives the cost of the generation for the cell plus one half the total saving of all the purchases. In this case, assuming that a pool control center exists, the cell prices would be computed by this center and would differ from the prices under multiple interchange contracts. The order in which the interchange transaction agreements are made is very, very important in costing the interchange where there is no central pool dispatching offices. Such analysis is required by federal and state agencies in most of the nations. For example, consider a three-party transaction, COA, locates power and energy in COC and makes an arrangement with an intervening system of COB. So there is a case between A to C and there is an intermediate agency at B point for transaction. So then COC sells to COB and COB sells to COA. The price level to COA may be set as the cost of COC generation plus the wheeling charges of COB plus one half of COA savings. It may also be set at COB, net cost plus one half of COA savings will be the final cost. So price is a matter of negotiation in this type of transactions when prior agreement on pricing policies are upset. Often, utility companies will enter into interchange agreements that give the amount and schedule of the interchange power but leave the final price out. Instead of agreeing on the price, the contract specifies that the system will operate with the interchange and then decide on its cost after it has taken place, because you will get a clarity how much the incremental cost would behave after you physically extend the transaction. By doing so, the system can use the actual load on the system and the actual unit commitment schedules rather than the predicted load and committed schedules. Even when the price has been negotiated prior to the interchange, just assume that you agree to a price without any practical exchange of energy, utilities will many times wish to verify the economic gains projected by the performing after the fact production cost. Sequence of calculation impacts is long and subject to interpretation if the contracts are not all inclusive procedures. Assumptions on relative cost and fuel must be avoided, as well as assumed cost of transmission system use. Power systems are often interconnected with many neighboring systems, and interchange may be carried out with each one. When carrying out the after the fact production cost, the operation offices must be careful to duplicate the order of the interchange agreements. When several two-party interchange agreements are made, the pricing must follow the proper sequence. The central dispatch of a pool can avoid this problem by developing a single cost rate for every transaction that takes place in the given interval. So thank you all for your attention, and we covered whaling very nicely today, and most likely we'll talk about a pool market model when we meet next time. Thank you.